So today we're going to cover Chapter 6, Section 2. Today we're going to talk about bisectors of triangles. So yesterday we saw what a perpendicular bisector was, what an angle bisector is, and now what we're going to do is put them inside triangles. And we're going to learn about the points where all of the perpendicular bisectors meet and where all of the angle bisectors meet. So let's go ahead and look at a definition. So we're first going to define what concurrent lines mean. Now, it could also be three concurrent rays or three concurrent segments. Whenever they're talking about concurrent lines, what they're referring to are three or more lines that are going to all intersect at the same point. So if I draw three lines here, actually I'll draw four. It has to be at least three. They're all going to intersect or cross at the same point. So if I keep drawing lines, so I need at least three. So I got three here. I could draw in a fourth one if I need to, but let me just stop here. Now, the point where all three or more of these lines cross is called the point of concurrency. So in this picture, my point of concurrency would be located right here. So it's that point, or it's going to be that ordered pair where all three lines meet. So if I were to have graphed this on a coordinate plane, I'm going to be looking for an ordered pair to find my point of concurrency. So the purple is my point of concurrency. So again, concurrent lines are just three lines that are graphed, three or more, and they're all going to intersect at the same point. So let's see how we're going to apply this concurrent lines definition. And we're going to learn the Circumcenter Theorem. And the Circumcenter Theorem, or the circumcenter of a triangle, is going to be the point that is going to be equidistant from the vertices of the triangle. So what this circumcenter actually is it's going to be the point of concurrency of the three perpendicular bisectors. So in this picture, all of the blue lines are the perpendicular bisectors. So everything that's in blue on this graph, these are the perpendicular bisectors. Now, without any right angles or congruency marks, I can't tell for sure unless they tell me that these are the perpendicular bisectors. So if they don't specifically tell you, they would also add in that there would be a right angle here, indicating that it's perpendicular. Also remember, a bisector splits the segment that it's bisecting into two congruent pieces. So this could tell me that this segment is congruent to this because point F is going to be my midpoint. Over here, same thing. AD is going to be congruent to DB because, again, PD is the perpendicular bisector, so I know D is the midpoint of AB. E is going to be the midpoint of BC, so that would split this into two equal pieces. So this is how you might be given the information that PD, PE, and PF are the perpendicular bisectors. They're either going to state it like I did here, or they're going to add in the congruency marks and the right angle. Once we establish that we have those three perpendicular bisectors and their point of concurrency, or the point where they meet, this point P, from this point P, I can draw these red segments that are going to be equally distant to each of the vertices. So from that point P, I could draw out a segment going into vertice A, B, and C, and all of these red lines are going to be equidistant, so they're all going to be congruent. So notice how they put PA equals PB, which equals PC. So all of the red lines in this picture are all equidistant segments going in to each one of the vertices. Blue segments are the perpendicular bisectors, and the red lines are all the equidistant segments that are going to go from the vertices. So they're going from the circumcenter, which is that point of concurrency of the perpendicular bisectors, and they go out to each vertice, and they're all equal. Now, the perpendicular bisectors are not equal, but the point from that circumcenter to the vertices, those red ones are all equal segments. Let's look at the location of the circumcenter on the next slide. So this point of concurrency, where all of your perpendicular bisectors meet, when you have an acute triangle, it's always going to be located inside the triangle. When it's a right triangle, that circumcenter will be on the triangle. And when it's an obtuse triangle, it's going to be located outside of the triangle. So whenever they're asking you to draw, or maybe you're trying to get a visual for yourself, whenever you want to draw a perpendicular bisector, you're going to find the midpoint of the side, and then you'll draw in that perpendicular segment. Now, when I'm asking you to find the point of concurrency when it's an acute or an obtuse triangle, they're going to be more challenging than the right triangle. More than likely on your test, I'm going to give you a right triangle, because all you have to do is your perpendicular bisector is going to be a vertical or a horizontal line. And we're going to do that on the next slide. So find some way to memorize where the circumcenter is located, because we're going to be learning several different points of concurrency. I'm probably going to give you sometimes, always, or never questions based on these points of concurrency. So whether you use an abbreviation of letters to help you remember, like for me, I would say, okay, it's an acute triangle, so I'm going to use the letters AI. So acute, it's inside. For the right, I would say like the phrase right on. So it's right is located on the triangle, and obtuse is outside, so I could say that that's OO. If you want to just, and remember this is outside. So obtuse is outside, but the right is on. So this is where it could get kind of confusing if you used RO. You might not know if that means outside or on. So right on, and then, but whatever trick's going to help you remember. AI is acute and inside. But whatever trick will help you remember. Just remember the circumcenter when it's an acute triangle. Once you draw in those perpendicular bisectors, you're going to see that it's going to be located inside the triangle. When you draw the perpendicular bisectors of a right triangle, it's always going to be on the side, on that hypotenuse of the right triangle. And then when you draw all of them in an obtuse triangle, it's going to be located outside of the triangle. So just find a way to memorize the location. Now, another vocab word is the word circumscribed. So here, the circle with center P is said to be circumscribed about the triangle. Whether you think of, when you see the word circumscribed, think that the circle is outside of the figure that's being circumscribed. So it's outside of that triangle. So just a vocabulary word. Okay, so next we're going to find the coordinates of the circumcenter of a right triangle. So I'm going to walk you through step by step. More than likely, this next example is what you're going to see on the test or on the quiz. So pay close attention. When you're doing the homework tomorrow night, this will be the type of question I'm going to give you. Okay, so here we go. Step number 1, when we want to find the coordinates of the circumcenter, is going to be graphing the coordinates for A, B, and C. So I'm going to go ahead and graph point A. It's at 0, 3. I'm going to graph B, 0, -1. I'm going to graph C, 6, -1. I'm going to connect my points. So that's step number 1. So go ahead and put down this step by step. So step 1, graph it. Step number 2, I need to find the equations for the perpendicular bisectors. So I need to find the equations for the perpendicular bisectors. Now again, if your triangle was acute, then this would be a more involved step. But this is actually what we're doing with number 10. We need to first find the midpoint, because remember the perpendicular bisector is going to hit at the midpoint. So the first thing I'm going to do to find this equation is I need to find the midpoint of sides AB. To find the equation for the perpendicular bisectors, I need to find the midpoints of the sides. Now, when I'm doing a right triangle like this, I'm only going to find the midpoint of AB and BC. Once I find the perpendicular bisectors for those, because it's going to be a lot easier to find the equation of the line when it's a vertical or horizontal line. I could find the midpoint of AC as well, but as soon as I fill in two of the perpendicular bisectors, the point of concurrency of that third perpendicular bisector is going to be the same spot. So if I find the midpoint of AB, remember your midpoint formula, x1 plus x2 divided by 2, y1 plus y2 divided by 2. So what I need to do is add 0 plus 0, divide by 2. I'm using the order pair for A and B. And then I add the y's, 3 plus negative 1, divide by 2. This gives me 0 over 2, 2 over 2. So the midpoint is the order pair 0, 1. Let me go ahead and put in my midpoint here. Then I'm going to do the same thing for BC. I'm going to find the midpoint of that. Again, I'm using the two coordinates, B and C. So 0 plus 6, divide by 2. Negative 1 plus negative 1, divide by 2. 6 over 2, negative 2 over 2. And my midpoint is 3, 1. So I'll go ahead and plot that one as well. Sorry, 3, negative 1. So let me plot that one. Now I could also do the midpoint of AC. So if I add A and C, 0 plus 6, divide by 2, and 3 plus negative 1, divide by 2, 6 over 2, 2 over 2, order pairs 3, 1. Now what I need to do is find the equations of the lines. So we could also use our I could use the slopes of perpendicular lines theorem. And this is what you're going to do when you do number 10. However, I just know that whenever I have a vertical line, so AB, the perpendicular segment is going to be a horizontal, and it comes out of that midpoint. So here's my first perpendicular bisector. Then for the perpendicular bisector of BC, it's going to be the vertical line. And I can already see my point of concurrency without even drawing the perpendicular segment of AC. I can already see my point of concurrency is this order pair 3, 1, because it's always going to be located on the right triangle. But just to go through officially and come up with these two equations of the perpendicular bisectors, remember whenever it's a vertical line, this is actually the equation of x equals 3. And then this one right here is going to be y equals 1. So whenever it's a right triangle, it's super easy. And then you just find the point of intersection of those two lines of y equals 1 and x equals 3. And it's that order pair 3, 1. So once we find the two equations and we found the midpoints, we know that the line through that order pair, 3, 1, that's perpendicular to BC, is x equals 3. And then the same thing through midpoint AB, so the line through the order pair 0, 1, and that's perpendicular to AB, is y equals 1. So that's for this one, and that's for this one. So then now what we need to do is find the point for step 3. So we find the point where x equals 3 and y equals 1 intersect. And that's the ordered pair 3, 1, which equals our circumcenter. So honestly, whenever you do this, if you graph it and all you do is find the midpoint and then draw from that midpoint a vertical line and a horizontal line, see where those vertical and horizontal black lines meet, and that's at that ordered pair 3, 1. So this is why I'm going to give you a right triangle versus an acute or an obtuse, because those are going to get more challenging. But you can always practice it. Again, whenever you're doing this, I definitely recommend you rotate your iPad. I may give you a worksheet where I'm going to make you practice drawing them, but we'll see how that goes. So this is how you could find the circumcenter of a right triangle. Remember, the right triangle circumcenter is always located on one of the sides of the right triangle, and it's the hypotenuse. When it's an acute, it'll be located somewhere inside the triangle, and when it's an obtuse triangle, it'll be located outside. And we would draw these perpendicular segments. So for the incenter of a triangle is going to be equidistant from the sides of the triangle. So in this picture, it says if AP, BP, and CP are the angle bisectors of ABC, then that tells me that PD, PE, and PF are all going to be equal. So in this picture, in red, these are all the angle bisectors. So they're either going to tell you that they're the angle bisectors, or they'll have congruency marks on the angles, showing that this angle is congruent to this congruent to this, and then this one congruent to this. Now, these angle bisectors are not equidistant. They're not congruent segments. However, from the point of concurrency, from this incenter point, I could now draw out the blue lines, and all of those blue lines are going to be equally distant from the incenter to the sides of the triangle. Now, these blue lines are not the perpendicular bisectors. Point D is not the midpoint of AB. All it is the distance from the purple point to the side. And these are all equal segments. And that's what your incenter theorem states. So all of the blue lines, so all the blue segments are congruent. They're all equidistant to the sides. So they go from the incenter to the sides. So from the point of concurrency of the angle bisectors out to the sides they're all equally distant. Perpendicular bisector is going to hit at the midpoint of the side of the triangle, and the angle bisector is going to bisect the angle. So look for these congruency marks. Let's see what the incenter is. So the incenter, again, is the point of concurrency of the 3 angle bisectors. So in this picture, the red lines are the angle bisectors, and the point where they're all meeting, right here, this is the incenter. So the point where all 3 angle bisectors meet. Now notice this time in the picture, they've got the congruency marks showing us that those red lines are angle bisectors. They did not draw in those equidistant segments in this one. Unlike the circumcenter, where it sits in different spots depending on the type of the triangle, for the incenter, it's always going to be inside the triangle. So this one's easier to remember. So maybe think of the word in center. So it's always inside the triangle. Another vocab word down here, the word inscribed. Here in this picture, the circle is said to be inscribed within the triangle. Now the circle's inside it. Before, when it was circumscribed, it was outside of the triangle. So just understand these vocabulary words. Now let's just do some examples, or just one example, and we're done. Okay, so in the figure shown, it says that ND is congruent or is equal to 5x minus 1, and NE is equal to 2x plus 11. It wants me to find the length of NF. Now let's go ahead and figure out what these blue and red lines are. So in this picture, we can see that all of the red lines are the angle bisectors. Notice the congruency marks showing that angle B was bisected, angle A, angle C. All of the red lines or red segments are the angle bisectors. I can see that point N here, that's right smack in the middle where all of those red segments are meeting, that's my incenter. Okay, so N is the incenter. And remember, the incenter is the point of concurrency of the angle bisectors. So if N's the incenter of triangle ABC, that tells me that those blue lines are all going to be the equidistant segments. So since N is the incenter, which is just to review, the point of concurrency of the three angle bisectors, then the blue lines, or the blue segments, these are going to be the equidistant segments from the incenter to the side, to the sides of the triangle. So I could add congruency marks to these blue ones because these are all the perpendicular distances. Now that other blue line that's diagonal, we're going to wait on that one. So the equidistant segments are all these. And again, we can tell they're a distance because they're perpendicular. Don't confuse these with the perpendicular bisectors because D, E, and F are not midpoints. So these are just the equidistant segments. All right, so this was just a little bit of background knowledge. So now to find NF, so since I've just added in those congruency marks, I now know that ND is equal to NE, which is also equal to NF, which is what it's asking me to find. But if you notice up in the problem, they only gave me information about ND and NE. So that's what I'm going to use to find X, and then I can plug it in to find NF. So I'm going to set ND equal to NE, so 5x minus 1 equals 2x plus 11. I'm going to solve for X by subtracting 2. 3x minus 1 equals 11. Add 1. 3x equals 12. Divide by 3. And x equals 4. Now remember, it wanted me to find NF. So once I get x equals 4, I can plug it back in to either ND or NE. Because remember, ND, NE, and NF are all equal. So let me go ahead and plug it in, and I'll show you I get the same answer either way. So if I plug it in for ND or NE, doesn't matter. So 5 times 4 minus 1, 20 minus 1, I get 19. Or if I plug it into NE, 2 times 4 plus 11 8 plus 11, I get 19 either way. So again, remember, ND, NE, NF, they're all equal, and they all equal 19. So that was the answer to part A. Now for part B, it said, can NG, and that was this other blue segment that was here. So let me change the color on it. Let's make it pink. Change the color. Okay, so NG is right here. Now, if you recall back from chapter 3, when I talked about having the banks of a river and you want to get across it the fastest way or the shortest distance, remember that shortest distance is always going to be the perpendicular distance. And I've already found that perpendicular distance. That was NF. And NF is 19. So if this is 19, then this other segment that's diagonal, the NG, it can't be smaller than 19. So this is why part B, NG could not be equal to 18 because the shortest distance was the NF. Now, you could also think of this as being like a little right triangle here and think of NG as being the hypotenuse. And remember, the hypotenuse is always the biggest side. So for part B here, we're just going to state that the shortest distance between a point and a line is always the perpendicular segment. And in my picture, that perpendicular segment was either the NF, the ND, or the NE. So, and because my NF equaled 19, 18 is less than 19. So because it had to be a longer distance, this would not happen. So 18 is not equal to 19. So NG could not equal 18. It would have to be bigger than 19. And that is it for the notes on section 2 of chapter 6.